Okay, let's test yourself. Let's try some practice questions. The first one being, all atoms of the same element have the same number of what? You said protons? You're correct. Next one, the smallest unit of an element is A or An. Did you get atom? Then you would be correct. What about what are the subatomic particles of an atom? Protons, neutrons, and electrons would be the correct answer. And last but not least, what term is best used for this definition? Each of two or more forms of the same element that contains equal numbers of protons but different numbers of neutrons. You got isotope? You're correct. So now that we've reviewed, let's talk more about molecules and compounds. A lot of atoms don't exist by themselves. They're not in a free state. They're generally chemically combined with other atoms. We can look at molecule and compound as just strict definitions, but the easiest way to think of molecule and compound is to know that a compound is a type of molecule. Molecule is more of a general term. It could be talking about atoms bonded together that are of the same type or of different types. For example, oxygen gas is a molecule but not a compound. Water is a molecule and a compound because a compound is a more specific molecule and it's only used to talk about a type of molecule that has two or more different kinds of atoms bonded together. We can also look at mixtures. Most matter exists as mixtures, like sand and water, where we have two or more components physically intermixed. Examples of mixtures are solutions, colloids, and suspensions. Solutions have small solute particles that are evenly distributed throughout. We would consider solutions something called a homogeneous mixture. Mineral water is a great example. Colloids have solute particles that are larger than what we see in a solution. They can scatter light and they do not settle out. A great example is something like fruit jello. Depending on how you store it, it's not going to be evenly distributed throughout the jello. That fruit might be up at the top or down at the bottom. Both colloids and suspensions are considered heterogeneous mixtures, where the solute is not evenly distributed throughout. Suspensions have even larger solute particles than what we see in colloids. They do settle out. They can or may scatter light. A great example of a suspension is a blood sample. Leave it alone for a long enough period of time, and the components will settle out into plasma and red blood cells. So let's define some terms before we go further. When looking at a solution, you're looking at the only homogeneous mixture. A homogeneous mixture means that the particles, the solute, are evenly distributed throughout the solvent. Well, what's the solvent? It's the substance present in the greatest amount, like water. It usually does the dissolving. A solute or solutes are substances that are usually present in smaller amounts, usually get dissolved, like sugar or salt. A lot of true solutions in the body are transparent, like salt and sugar solutions in the blood. Colloids are heterogeneous mixtures, just like suspensions. Colloids are also known as emulsions, and they can undergo something called a sol-gel transformation. A sol-gel transformation is when a solution, a liquid, goes to a gel. You see that with Jello, but you can also see it in the liquid component inside of cells called cytosol, going from a solution to a more gel-like consistency. Suspensions, like colloids, are also heterogeneous. They do have solutes that settle out, and blood again is a great example. Sand and water are another example. So let's compare compounds to mixtures. The biggest difference is that compounds are chemically pure, whereas mixtures are composed of two or more components. You cannot separate compounds by physical means, but you can mixtures. And compounds are always homogeneous, whereas mixtures can be homogeneous or heterogeneous. When you're looking at mixtures, the only homogeneous one, though, is solutions. Let's take an example, salt water. It is a homogeneous solution with salt evenly distributed throughout. And if you were to take a kind of a screen cap or screenshot of a solution to be able to look at all of the solute particles within a solvent, you should have an equal distribution because it's homogeneous. In salt water, as our mixture, what is the solvent? The solute? If you said water was the solvent, you'd be correct, and the solute in salt water is the salt, or sodium chloride. But don't forget colloids and suspensions. Those other two mixtures, they're both heterogeneous, whereas colloids are also known as emulsions. They're the only ones that are able to undergo sol-gel transformations. So there's three main differences between mixtures and compounds. Mixtures do not involve chemical bonding, but compounds do. Mixtures can be separated by physical means, but compounds cannot. And mixtures can be heterogeneous or homogeneous, whereas compounds are only homogeneous. Let's also take a quick look at some of the concentrations of solutions. You want to be familiar with these because you'll see them throughout your textbook, like percent or parts per 100 parts. That's a solute percentage. Or milligrams per deciliter. That could be used for glucose measurement or cholesterol count. Or molarity, moles per liter. 1 mole of a substance is equal to its atomic weight. And if you know the atomic weight or mole of a substance, you know what weight has 6.02 times 10 to the 23rd power molecules, which is Avogadro's number. We could talk a little bit more about molarity. And to do so, let's calculate molecular weight for water. Water has 2 hydrogen atoms and 1 oxygen atom. So if we look on the periodic table, the atomic weight for hydrogen is about 1.01, and the atomic weight for oxygen is about 16. Now I only have 1 oxygen atom, so that's 16 times 1 is 16, and I have 2 hydrogen atoms, and that's about 1.01 times 2, so that's 2.02. If I add 2.02 and 16 together, I get 18.02. So that gives me the molecular weight for my compound water. So I want to tie it all together. If I know that 1 mole of a substance is equal to its molecular weight, I know that 1 mole of water is equal to 18.02 grams. And in 18.02 grams of water, I have 6.02 times 10 to the 23rd molecules. That's how I could use molarity. Molarity is also reported as a capital M. If you want to do another example, you can look at how to calculate molar mass here for this example atom made up of a hydrogen, carbon, oxygen, and chlorine. You just look on the periodic table and get their atomic weight, add it all together, and represent how many of each is present in that particular compound, and you'll get the molar mass, or something known as atomic weight, for that compound. One of the next topics we're going to be looking at are chemical bonds, and chemical bonds are going to be either ionic, covalent, or hydrogen. The hydrogen bonds are a little different from ionic and covalent, but we'll talk about them while we talk about the other. So make sure to watch that video.